Thank you very much for being here today and welcome to this collaborative workshop. So today we're going to talk about new technology and new technology in precision forestry. And so we get the chance to have two passionate speakers with me today. So Kevin Toderel, which is from RMUS, he is the general manager, and Jean-François Prieur, who is the project manager at CERFO, and myself, Bastien Vandendaele, which is a researcher at NHRI. And so we built the workshop into three parts. And during the first part, Kevin is going to do a showcase of technology because we are going to show you how to use this technology. So the first part will be dedicated to a little showcase about UAV, mobile laser scanning, and other types of technologies. Then I will be taking the talk and talk about mobile laser scanning and UAV laser scanning and how to process the data from raw product to useful product. I will show you a lot of different interactive video. And then Jean-François Prieur is going to finish talking about species, AI, and different type of satellite data, more particularly the planetscope data, and how to process them to get a useful product for foresters. Thank you very much, and I'll let the room to Jean-François Prieur. Thanks.
Hi everybody, my name is Jean-François Prieur. I work at CERFO, which is a research center associated with the Cégep de Sainte-Foy near Quebec City in Canada. I'm going to be presenting some work. I started working in May at CERFO, so the first part of this presentation was done by my colleagues Mathieu Varin, Bastien Vandendaele, and Jean Marchal, and they're trying to predict dominant species using machine learning and multi-temporal optical imagery, first in Quebec, and then the project that I'm more associated with, along with NHRI, doing the same thing in New Brunswick. I can't wait to not start my presentation with this sentence. Species identification at an operationally accurate level is still a challenge. I think I said that in 2016 at an AWARE conference, and it's still the first bullet on my presentations. My background is in airborne laser scanning and species identification, and I believe like a lot of, and I've been working in technology in general for about 30 years, and ALS, like many new technologies, was perhaps oversold as the answer to the species question by academia and some researchers, and I include myself in this group, if you let me editorialize for a second. I was working in Ontario in 2021 with the new single photon LiDAR data, and I was hearing people at conferences saying, single photon LiDAR will get species, and I was like, no, it will not. There's not a magic thing in a single photon LiDAR pulse that will get you species. So there's this disconnect between some of the scientific and technology marketing and the realistic problem of finding species in the complex forest environment that we're in Canada. So are we looking at the problem in a realistic manner? And this is some work I did, individual tree segmentation for JDI during my graduate studies, and it looks great. It's a spruce plantation with some hardwoods, but once you try to generalize it and try to get, especially for the hardwoods, it gets very complicated, and it doesn't perform that well if you get into bigger and bigger areas. So perhaps taking a step back and saying, what kind of species information can we give? And every organization and every company will have a different problem that they're trying to look for. Some people want to find fir versus spruce. Some people just want percentage hardwood. I think we need to have a conversation between the data scientists and the people out with the boots on the ground and saying, how can we frame the problem to give you actionable information on species? And we talk a lot about AI. I'm more of a machine learning person. I did random forest because you put your data in and out comes the predictions. There's not a lot of tweaking. I'm a simple man. We talk a lot about deep learning, and I think that deep learning needs unrealistic amounts of training data to go to individual species. You need tens of thousands of examples of each class. Like if we're talking about Google and their neural nets of cats and dogs, they have 100,000 pictures of each. I think I had 5,000 training crowns in Black Brook, and that was done over 2-3 years, and that was a big, but for some species, I had like 45 exemplars. And it still kind of worked in the end. So I'm quite skeptical that just deep learning is the answer to all our solutions. The work that the CERFO did, you can find the report, it's in French. It was done in 2021. It's in the Abitibi-Témiscamingue region of Quebec. And they were using planetscope 4-band imagery, now we're at 8-band, 3 meter, and Gouvernement du Québec airborne LiDAR scanning data, and photo-interpreted training crowns. And they were doing it for 9 species. And they were using a machine learning approach where they also tried to evaluate gradient boosting, random forest, and tried to see if there was one that performed better than the others on this problem. This is how the training data was generated. So as I said, some photo interpreters from the Quebec government tried to identify pure populations of each of the species that we were looking at. They would draw a polygon, and then what we do is we would shrink the polygon to really make sure that we're zooming in on the proper pixels, and then extract points, and for each of those points, extract from the planet the pixel values for the 4 bands and the ALS features that we were using. As you can see, the training sample distribution is extremely unbalanced, which causes issues, and you have to use balancing methods when you're doing machine learning. So ideally, you'd like a much more even distribution, because if you don't do anything, the majority classes get really good classifications, and the minority classes get not as good. If you ever worked with planet imagery before, it comes in strips, and scenes are composed of these strips. Sometimes they align. You get the same scenes like in the spring and in the fall. They aligned along the strip. And sometimes for the summer imagery, it doesn't. So that's when, if you're used to working with Sentinel-2 imagery, like I am more, when you look at planet imagery, it's a bit of a shock, because even though the resolution is nicer, radiometrically, it's not as nice as Sentinel-2, you know, a nice tile and everything is clean. But it has the temporal revisit advantage of flying over your area of interest every day. So that's a non-negligible advantage. So there's a lot of work to do in harmonizing and normalizing these different strips. So we would take spring imagery, summer imagery, fall imagery, and ALS features, extract for each training point the values, put that in the machine learning classifier, random forest gradient boosting, and you would get a species map at the end. As I said, you have to normalize the planet scenes. So this is just a random screenshot I took where you have 3 different Dove satellites. It's pretty clear. You see the striping, because even though they can be part of the same constellation, but every planet satellite is slightly different than the other from a radiometric perspective. So you have to deal with, there's also, I think, a seam in the middle. You got half a cloud. So there's other challenges that come with that temporal revisit rate. That's an advantage. So how most people kind of harmonize this is they do a modal method, or a majority pixel. So we had 3 images, and so whichever pixel value came up more, the median or the mode, there's different approaches, that would be in the mosaic, that would be the value that we would take. So let's say you have 100 scenes, specific period of time, you figure that the mode or the median will be the most representative value for that pixel. I don't want you to memorize all this. There's no quiz at the end of this. It's just to show that this is just using our open source method. There's nothing, it's just your basic train set, test set. You send it to the classifier. You identify the more important features, and then you do your predictions. And then there's some post-processing, the lakes, the roads, punch out things, trim everything at the 95th percentile. That's what they do in Quebec. So it's all using free and open access tools. The results in the lesson learned, I won't bore you with confusion matrices and stuff. It's just to say that there was an acceptable amount of accuracy overall. It was 83% on the 9 classes, but there was a lot of commission and omission in certain classes, so you could not probably deploy this operationally. But it did show that the planet scope, you could try to use it, but by itself, it's not enough to really get operational. The use of photo interpretation to label training pixels, it's probably a waste of their skills, and this limited and scarce resource is needed in other areas. So I think if we can find another way to label pixels without using photo interpreters, I think that would be an advantage. We need a quicker method to generate larger amounts of training data. As I said, deep learning requires unfeasible number of pixels, and the image nets that everybody talk about, they require 32 by 32 square patches of training data. So if you think Sentinel-2, 10 meters, that's 320 meter by 320 meter of pure one species training data that you have to find. So and I'm sure I'll be proven wrong in a year or two, because there'll be sparse methods maybe for deep learning, but right now, I really don't think going down the deep learning approach for species is the way to go. just from a resource standpoint and a time standpoint. The project that I'm now involved in with the Northern Hardwoods Research Institute is can we use other sources of imagery, aerial, ESRI base maps, other, Sentinel-2, in combination with PlanetScope to label training data to then train a classifier on a scene and then do species prediction on that scale. So we're leveraging domain expertise instead of photo interpretation. So about 10,000 labeled 10 meter by 10 meter, so based on the Sentinel-2 grid, they exactly align on Sentinel-2 pixels, were generated by NHRI in 2 weeks of work. So yes, it's not tedious work, but it's fastidious, and but it's not 2 months. So we can generate a fair amount of training data that way. And it's just 3 species group for the moment. We have balsam fir, spruce, and other. And also another piece of information that we're going to try to do is first we're going to try to do the 3-class classification and then try to predict the dominant species percentage in that pixel. So if we say it's balsam fir, we'll also try to say it's 80% balsam fir in that pixel. We're going to try to use additional features than just the spectral, some contextual. I've been hearing about contextual data for a long time, soil maps, species affinity, DTMs. The problem with that, when you were using more classic approaches, is when you're using different resolution rasters, if you're working in R and you're just sending in rasters, at one point your resolutions don't match, you have registration errors, it gets very complicated. When you're just extracting point values for, okay, so in the Sentinel-2 image, you have 10 values for each band. In the LiDAR, you have that feature. It doesn't matter about the resolution because you're just extracting the value for that pixel only. So it'll be very easy to add multi-temporal data, contextual information, and we're not going to use any LiDAR features, not because I don't like LiDAR and I was traumatized by my past experiences, but it's just we can't count on it being present all the time. But it can be very useful for topographical variables and stuff, so we will use some features derived from LiDAR. And we're going to use Sentinel-2 imagery when possible because of the superior radiometry, but in combination with PlanetScope, which is now up to 8 bands, and there's 5 common bands, I believe, between Sentinel-2 and Planet, so you can kind of combine them. So the initial classification done by NHRI showed promise. On a single date PlanetScope mosaic, there was acceptable initial accuracy across the 3 classes, and it showed that the approach had potential. So NHRI and CERFO established a partnership to try to work together and improve this modeling and try to provide some actionable information. And I'm also trying to level advances in machine learning. So as I said, maybe 6 years ago, 2015, I didn't know how to code in Python and R. I'm still not a developer. I know just enough to be dangerous, and but the tools that are available at our disposition now, especially in ensemble learning now. So before you would create one random forest classifier, and that was your result. Now, with a concept called AutoML, auto machine learning, and a Python package called AutoSKLearn, in very few lines of code, we can get an ensemble model. So I'll go through it a little more in detail. So at the top is the data frame that you would send to your classifier. So the first one is the category of the pixel. So we have either 1 balsam fir, 2 spruce, or 3 other. And then all along, so 1 row is 1 pixel, 1 training pixel. And now here's an example of some spectral indices where you could have a bunch of other features. So that's what you're sending into the classifier. And then in a few lines of code, it will generate your test set, your training set. And then at the end, instead of having 1 random forest model, it starts with a gradient boosting model, and then it learns from that and tries to, okay, where did it go wrong in this model, and train the random forest. So it tries all these permutations that you could do yourself, spending hours just changing variables in front of R and making mistakes. This took, I think, 20 minutes to train, and you can put, no, sorry, 600 seconds, 10 minutes. So at the end, it makes an ensemble of 8 models, and then you just use that, like a random forest model. You can predict the pixels on it, but the accuracies are about 5 to 10% higher than just a random forest model. I did not put accuracies on here because I'm waiting to validate this model. NHRI has 3,000 validation pixels that I don't want to know about, so I didn't want to put, this model said it was maybe 92% accurate on the training data, but I don't expect that to generalize as well. But if we get in the 80%, then we know we're going down the right road. It's also, instead of starting from an initial model with no knowledge, they've trained all these random forest models, these gradient boosting, on existing data sets, and a bit like they use image nets trained on other image, you can use that at a starting point. It kind of starts your model at a, not a 0, but at a learn state. And you can turn all this off and just do, give me the best model that you found after 20 runs, if you want to try it that way too. It's very customizable. It's just, for me to do this even 3-4 years ago would have taken me a month or two. Now you can just do it, you know, you can try different models, different features, different thing, and just spend your time doing the data science and not the computer programming, which for me is quite boring. And it's a fully open source approach too. It uses R or Python. You have to talk about ChatGPT today. It's very useful for me into turning ideas into code for somebody who doesn't have a coding background. It's not perfect, but it's pretty good when you ask very precise questions. I also asked it, can you identify tree species at individual tree level with airborne LiDAR? It waxed philosophical for about a page with no useful information. So for that type of problem, it's not that great. But for codes, you know, can you extract per pixel band values to a CSV file with a band in each column in Python or R? And the code it gave, I had to tweak it a little bit, but I would have read 12 Stack Overflow pages before getting to the answer, and now I just have it on one. So it's a bit of a time saver. I'd like to end my talk on an optimistic note. Everybody who knows there's going to be, I think, potential difficulties in acquiring optical imagery in this summer because of the forest fires. And smoke and haze is prevalent in all the June and July imagery that I've seen. Haze is almost worse than clouds. Clouds you can detect and block those pixels and mask them. Haze is all over the image. This is where the PlanetScope daily revisit rate may be really advantageous and may be the killer app, because Sentinel-2, I believe, is 5 days, but sometimes for a full scene can be up to 2 weeks. So just end with a little show and tell. Love a nice Sentinel-2 reflectance image. It's really nice when it comes out. That was May 29th. So this is an image that we've done an initial classification on and is waiting for validation. If I look in June 24th, and I've looked pretty much every day since then, this is what it looks like now. So it might be an issue for people using, might need the drone. That's what's gonna happen. You need all the scales to do things. And hopefully the Planet, since they have common bands, we can maybe train a common model and get around this. But the Sentinel-2, can I go back? Yeah. I mean, Sentinel-2 radiometrically, and because of the 10 bands, will always provide better data than Planet. And I think that's the end of my talk. Thank you.